Welcome to the second part of the 3D Gravity Simulator adventure. If you missed the last one, you can either watch it right now by clicking on the little card on the top right corner of your screen, but if you do so, please come back afterwards so my watch time doesn't get ruined, or you can just stick around as I'll quickly recap what I did in the last video. So basically, the goal of this mini-series is to create a program that allows us to visualize gravity in 3D space without using any existing 3D rendering engine or physics engine. So I'm developing this entire project in C++ using the OpenGL API for rendering. In the last video, I quickly explained how Newton's law of universal gravitation can be used to simulate gravity and talked about rasterization, the algorithm that allows us to draw three-dimensional objects on the screen. To achieve this, we basically had to flatten out our 3D objects after transforming them in several ways, and then fill in all the triangles which compose their models. This is how far we got in that episode, which might look a bit underwhelming, but now that we've got a working rendering pipeline, it should be much easier to add new features. Today, I want to add camera movement and some simple user interface to the simulator, so we can at least play around a bit without having to change the code. Also, please consider subscribing to the channel so you don't miss the next video, and don't forget to leave a like if this is the kind of content you want to see more of on here. Let's start with the camera movement. My goal is to add something similar to what most 3D applications use today, which I call an orbiting camera. In Blender, for example, we can focus one object and then orbit around it and drag the camera around using the mouse. That's the kind of movement I want to implement in my gravity simulator. To achieve this, we need a way to convert the two-dimensional mouse coordinates into a three-dimensional translation that we can apply to the camera. My first idea was to use spherical coordinates to move the camera on a sphere around the focused object, as spherical coordinates can describe a position in 3D space with only two numbers, and it would be easy to implement mouse wheel zooming by simply changing the radius of this invisible sphere. While this sounded great in practice, I just couldn't find a way to make it work reliably because I was mainly trying around different ideas based on examples and formulas I found online, and it just never worked out the way it should have. That is until I stumbled across this article which showed how to implement the same orbiting mechanic using a different method. The idea behind this post was simply to rotate the camera around the focused position using true rotation matrices. A rotation matrix is simply an elegant way to rotate one position around another on a specific axis using trigonometry. We can then use the mouse X and Y coordinates as angles for these two matrices, one for the vertical axis and one for the horizontal axis. That method turned out to work nicely, so if you're interested, I've linked the full article in the description, along with other resources I used to make this video. Zooming was pretty easy to implement, as I just had to move the camera closer to or farther away from the focus position, depending on the mouse wheel's scroll direction. Dragging, however, was a little bit more challenging. The idea is that we should be able to move the camera and its focus position by dragging the mouse across the screen, which is once again a question of finding the correct 3D vector from the 2D mouse coordinates. My approach to this problem was to save the mouse position in memory when we start to drag, and then use the difference between the current mouse position and saved start position to obtain a 2D screen space vector which we can then transpose into 3D world space, which can be done by multiplying it by the inverse of the view matrix. That might all sound really complicated, but you can just imagine it as if the screen was in the 3D world and then just moving the camera in the direction the mouse would be moving on that screen. With camera movement working decently, I added the ability to change the focused body by right-clicking on a different one, along with this little overlay to indicate which body is currently being focused. So that was probably the most complicated part of the video. If you have any questions about camera movement or anything else, don't hesitate to ask them in the comments down below, and I'll try to answer them all. Now let's move on and talk about user interface. Currently, the only way to mess around with the parameters of the simulation is to change the code, which isn't exactly user-friendly. I would like the user to be able to change parameters like mass, size and color of every object, as well as to mess with the simulation settings just by interacting with text fields, checkboxes and buttons. So how do we render UI? Well, as you know, everything we can render with OpenGL has to be made out of triangles, and that also applies to UI. The only difference is that we don't want to render it inside the world, but directly on the screen, above everything else. That obviously makes rendering UI much easier than rendering 3D objects, as we can skip all complicated transformations required to get the triangle screen coordinates, because all UI components should always stay at the same position on the screen, regardless of the camera's orientation. Therefore, we simply have to tell OpenGL where on the screen a specific UI component should be, and we then let a very simple shader fill in the triangles with the desired color or texture. Of course, we do have to split our components into triangles first, but in most cases, we'll just be using quads, which are always made out of two adjacent triangles. Really, the only difficult element to render is text, because we want to be able to draw any string of characters at a given size and color wherever we want on the screen. One way to achieve this is using a font atlas. We basically need one big image containing every possible character in a single font, and a file which tells us where we can find a specific character on that image, as well as its size and other information required to draw it at the right position relative to the last character. When rendering a piece of text, the engine then has to generate a bunch of quads for every character in the string with the right size and position. We then send the font atlas image over to the shader, which has to fill each quad with the correct pixel from the image, while of course discarding the background and applying the desired color if needed. In order for the shader to know which part of the image it should use, we need to specify UV coordinates for every vertex, which describe where these vertices should lie on the image. Despite being a little exhausting to get to work correctly, this method works relatively well. There is also an enhanced version of this technique known as distance field rendering, which also allows us to apply effects to the text, which you can find out more about using the links down in the description. Now that I had a way to render user interface, I started to implement various reusable components like buttons, checkboxes and text fields, all in their simplest possible form, as I am not a great front-end designer. What was important though was making the components work, which for most of them just requires detecting when they are being hovered and clicked on, and then executing the desired logic. For text fields, I also had to keep track whenever one was focused, and then redirect all keyboard input to it until focus is lost again. With all these components working, I went ahead and set up a panel to change the selected object's properties, and one for changing the simulation settings. I also added the ability to load and save a scene file. I'm currently just using a very simple binary format which stores the scene settings and objects along with their properties. At this stage, I really wanted to add shadows to the simulator. The problem is that unlike ray tracing, rasterization doesn't have an intuitive way to generate shadows in real time and instead relies on a technique known as shadow mapping. I had no prior experience with this technique, so I looked it up online, and from what I understood, shadow mapping relies heavily on approximations to determine which areas are in shadow, and it looked very tedious to implement correctly. It's also really bad at computing soft shadows, which would make things even more complicated. That's when I remembered another rendering method I tinkered around with in the past, known as Raymarching. With Raymarching, you can easily check whenever a point is in shadow, including soft shadows, as long as you have what's known as a distance estimator. A distance estimator is a function that returns a distance to the surface of the closest object anywhere in the scene, which is usually near impossible to compute efficiently in complicated 3D worlds. Luckily, the scenes in my gravity simulator are only made out of spheres, which makes the distance estimator really simple, because we just have to figure out which sphere is closest to the camera and then subtract its radius from the distance to its center. I don't want to elaborate on how Raymarching works just yet, as it could be the subject of another video, but I've once again linked some great resources in the description if you're interested. Thanks to Raymarching, we now have some nice looking real-time soft shadows. However, the light is currently just coming from a fixed point in the scene, which isn't really what I want. So instead, I added the ability to mark a body as emissive from the UI, which then turns it into the light source. I've also added a bloom post-processing effect to make emissive bodies glow, which is achieved by rendering the emissive body into a separate texture, which is then blurred and added back onto the main image. I then proceeded to add the last and maybe most important feature to the simulator, which is the ability to spawn new objects into the scene. The spawn position of a new object is obtained by calculating the intersection point of a ray going from the camera through the mouse cursor with an invisible plane containing the focused object center facing the camera. The initial velocity can be adjusted by moving the camera to another location, and to make it easier I added an orbit visualization feature which pre-computes future positions of the spawned object to predict its trajectory. It is also possible to tweak the object's parameters before spawning it into the world. And with that working nicely, I would say the first version of the 3D gravity simulator is now complete. So why did I decide to spend half a year working on this project, despite there already existing some much better alternatives like Universe Sandbox? Well, the short answer is because I wanted to. It's just really fun to work on these experimental projects and come up with your own ways to solve problems. I also believe that these kinds of projects are the best ways to increase your knowledge in a specific area, which in my case was rasterization with OpenGL and all the little techniques used here and there to make real-time 3D applications possible. So I suppose it's now time to thank you all so much for getting this channel to over 1,000 subscribers. It's amazing, seriously. I truly believe this to be one of the most meaningful milestones, especially for this kind of channel. And I know it's been 4 months since the last video, despite my best attempts to fix my release schedule. I would love to make videos more often, but these project videos just take a lot of time to make, which I don't really have that much of right now. I do, however, have some interesting ideas for future videos, so please consider subscribing if you haven't already. Don't forget to leave a like if you enjoyed, and I'll see you next time.